Okay, thank you. Thank you, Sonny. Yeah, so I'm going to give a post-mortem on a game that I made called AIIDE. For those of you who don't know what post-mortems are, they're a common genre of talk in the game industry. I'm sorry, right? They're a common genre of talk in the game industry. And they're about what the goals of the game were, how they changed over the course of the development and why. And so the standard after-action report, what went right, what went wrong, and lessons learned. And in particular, they tend not to be strictly focused on technical issues, but to actually engage in the aesthetic issues of the game, of like, was it fun, was it engaging, was it too hard, was it too easy, and even issues about the difficulty of the game development process. Now, we don't usually do postmortems in research. I think we should. We're in AIIDE games. Games is an aesthetic discipline. Aesthetics here I'm just using as a placeholder for the experiences of the player. But in the end, whatever AI you're building, its spec, its ultimate purpose is to produce a certain kind of experience in the player. And so that's got to be your ultimate evaluation function. We also are trying to build technologies that will be useful by people who aren't researchers. And so we also want to think about all the issues that are involved in actually building a game, having to get it used by non-researchers and so on. And so finally, when we do talk about our games, we tend to talk about just the technology and not talk about the aesthetics, and not talk about, especially not talk about the aesthetic failures of the games. And I think it is important that we talk about that. What we tend to do is we tend to talk about how great they are, and then we go off and have beer with our friends and then talk about why they aren't actually interesting to play. Just a little shout out. I'm going to recommend that you all go back and reread Damian Isla's original behavior tree paper, which isn't technically a postmortem, but it's a really great example of getting at the kinds of issues that I think we need to do a better job of getting at about what the actual needs of authors in interactive technologies. All right, so MK Ultra was an interactive fiction piece that I made that was trying to essentially be something facade-like, because it's been 10 years, over 10 years, since Facade was released. I wanted to make a mystery game that would emphasize dialogue, like real natural language dialogue, and puzzle solving with fully autonomous characters. They have planners and stuff in them. And then, because you're trying to tell a story, you still need something that's nudging you in the direction of the story. And so it had a facade-like beat system that was operating with it. And I worked on the game for a couple of years. It's on hiatus now. Because it was a technical success, it had cool technologies in it, but it was an aesthetic failure. And that's essentially why I wrote this paper in mind for this talk. It was experimenting with two core mechanics. One of them is natural language dialogue and question answering. And so you can walk up to any NPC and just start talking to them within the limited grammar and lexicon that it understands. And you can ask it questions, like where's Kavi, how are you doing, how do you remember the Illuminati? And you can give imperatives too, to any of the characters, the player character, the non-player characters, and say, search the house room without me, sit on the couch. And you can say things like, believe you're an orange, and then believe you are hungry, and then the character will eat themselves. Because the other core mechanic in it is belief injection. You can, as the player character, insert false beliefs into the KPs of arbitrary characters and change their behavior as a result. So that gets you puzzle gameplay. So one way of thinking about it is trying to turn AI debugging into actual gameplay. The underlying technology, it was scripted in Prolog, semantic parsing, using definite clause grammar. So it's essentially a 1980s era prologue program. It's 1980s era AI. And the research problem was how do we make a game out of that? Used a committed choice planner a la SOAR, and it had a bunch of cool exotic logics in it for tracking state information, for reasoning about social norms, and for reasoning about alignment and deception. It had a bunch of cool things that I never got to with area effect weapons. I went into make objects in the world that would cause everyone within a certain radius to change their beliefs. So there would be a riot control device, which was the deadhead bomb that would just make everyone suddenly chill out and want to smoke grass instead of break their bed. For both time reasons and AIIDE reasons, I'm not going to show a live demo, but I'm happy to show you a demo afterwards. But I do want to say, basically all I built in it was the tech demo. I fully built out the technical system, but the actual game really was just a tech demo. Your character, Bruce, was a spy. I'm sorry, this is no slide. And your MacGuffin is stolen, and you suspect your friend Kabi, who is also a spy, and who works for the other side of the Illuminati. You're trying to get it back, you go to visit Kabi, you're both being friendly to one another, and Kabi says, make yourself at home, but don't go into the bedroom. And so you're supposed to figure out that means it's in the bedroom, but if you go into the bedroom, Kabi will kill you. And so you have to find some way of disabling that aspect of Kabi's behavior so that you can recover the MacGuffin, and so you can do that in any number of ways. You can tell Kabi that he's orange and that he's hungry. You can tell Kabi that you're a plant, and so therefore Kabi doesn't care if you go into the bedroom because Kabi only cares if humans go into the bedroom. You can tell Kabi that you are a member of the Illuminati, and so he doesn't care because you're on the same side as him. So what went right was it was an interesting system to hear me give a talk about, or to watch me play. And the technology worked a lot better than I expected it to. Prologue really does turn out to be really great for just scripting simple symbolic AI systems. Definite clause grammars brought me a lot farther than I thought they would. Richard Evans' exclusion logic was really nice for maintaining state information in the knowledge base. And once again, autonomous characters do turn out to really just to be fun to poke and prod and watch what happens with them. And as we all know from Darius's talk, watching the failure modes is quite entertaining. And players also liked the fact that they didn't have to micromanage the characters. If they wanted to search the house, they weren't having to say, go to this object, go to that object, search it, go to that object, search it, go to that object, search it. You could just say, search the house, and the character knew how to do that. What went wrong was that the players couldn't understand how to play it. The biggest problem was they would just sit there and they would type stuff, and they would get near misses on its grammar. They would use colloquialisms that it didn't understand, and so they just sit there and thrash, trying to figure out what is something that's going to understand. And even when I sort of told them, no, it doesn't understand that, but it doesn't understand that, there was still a big problem of trying to guess my thoughts to figure out what I thought the puzzle was in order to solve it. There's also a lot of negative transfer from existing genres. It looked like a tile-based RPG, so people would try to navigate as if it were a tile-based RPG. It also looked like parser-based interactive fiction, and so rather than going up to Kabi and asking Kabi, how are you today, they would say, ask Kabi how he is today, or ask Kabi about MacGuffin. They would use IF-style interactions that were appropriate. So I think there are a couple of core problems that my game designer follow. One of them is that players have vast amounts of cultural knowledge, both in terms of game culture and knowing things about the genres and the tropes of particular game cultures and that produce negative transfer, but also players know vast amounts about the culture that these characters are pretending to inhabit, which in this case is basically North American white middle class nerd culture. And we know much more about that culture than the AI is ever going to know. But the game puts the player in the place of having to figure out what the subset is of that culture that the characters do understand. So the characters have almost no knowledge of that. And essentially, I'm putting the player in the position of having to be an ML system that's trying to learn what are the few kilobytes of knowledge about this world that the characters have out of the gigabytes or terabytes of knowledge that I have. If you think about that as an ML problem, it's going to require a lot of training data, a lot of interaction on the part of the player to be able to make that discrimination of what things does the character understand and what don't they understand. The other thing that I think is a problem with the game design was that we can think about a spectrum of AI characters with two extremes. One extreme is lifelike characters, where you're trying to make characters that don't seem like AI systems. And so we're trying to submerge the mechanical nature of the characters. We're trying to have them feel qualitatively as if they're characters in novels. And on the other extreme, clockwork characters, such as in The Sims, where we're trying to surface and foreground the mechanical nature of the characters. We want the players consciously thinking about their mechanical nature so that they can manipulate the characters. And that means those characters have to be simple enough that they're efficiently learnable by the players, whereas the lifelike characters, the simplicity is a problem. And essentially what the biggest problem with MK Ultra was that it needed its characters, because of the game design, to simultaneously occupy both extremes of that spectrum. And so on the one hand, it was trying to make them not look like AI and be very complex, so very human things, in order for it to be good immersive interactive fiction. And on the other hand, I was trying to have those same characters be the puzzles in the interactive fiction, and that meant they had to be super simplistic. And those two goals fought with one another. So lessons learned are that autonomous characters are still co-grounded, and surprisingly, you get symbolic AI is more performant than you would like. Logic programming, I really was surprised it worked out as well as it did. But players are really going to assume, are going to project a lot more intelligence into your characters than they have, and that has to be a focal design problem for your designing the game. And then finally, be careful about where you want to place your characters on the extreme spectrum between clockwork and lifelike characters. I think it's going to be really hard to make lifelike characters for the moment that use unrestricted natural language input. I fear that for the moment we're stuck with choice-based interfaces because it's just too hard to handle unrestricted ML for the lifelike characters. All right, thank you.
All right, so time for questions. Aaron.
Cool talk. Thank you for, as you said at the start of this, going back and looking at what you did aesthetically and for all those reasons. It's really appreciated. So I was thinking through this that I've had a trajectory sort of starting off more as an artist and ending up, in the computer science world. And I started originally making interactive stories that tried to be, like you were saying, with your characters, very seamless, right? Like not showing what the scenes were, not showing what was generated, what wasn't. And I really ended up in a place where I think showing something vital to help players understand how to use it, understand the system's doing right. So I'm curious if while you were developing this project, there were moments where you had an idea of how to expose something about how part of the system is working, and whether any of those experiments worked, why you did it, and try to think about that.
Yes. For me, the problem was how do you expose it in a way that wasn't intrusive. So like I had a debug screen, what were essentially debug screens. You could sort of jump out of the universe of interaction and look at the KDs of the characters and look at what the log from the problem solver was, which granted was never intended to be player facing in the end, but you know, trying to list out what are my current goals. There was a notebook you could look at that would remind you of what it was you learned and what you still needed to learn and what your goals were for this week and stuff like that. And then, you know, what would happen is the players just wouldn't find that, they didn't know what to do with it. I'm sure someone like you could have done a much better job with that than I did. But really what happened was I built all this great technology and I put it in front of the players, and the players just couldn't get started because the natural language interface was so painful for them, in spite of my doing all kinds of things with auto-completion and all kinds of prompting, and there were pie menus that generated automatically examples of likely kinds of things you might want to type, you could get up as a hinting system and so on, and none of it was enough. So, you know, I think really I needed to be working with a real game designer who would rein me in. And it needed not to be as technology-focused a project as it was. It needed to have someone controlling scope and controlling the aesthetic goals of it. Yeah?
I'm curious about your reaction to because you set it up with a very IF collaborative problem for them to solve. Do you think that played into it, and maybe if there was more of a theatrical framing, would that change the results?
Well, I think what I should have done was I should have either made a choice-based II game and thrown up the belief injection mechanics, or I should have thrown out its IF pretensions and made a traditional level-based puzzle game where first you have a puzzle that involves one verb and we tell you what the verb is, and then you have another level with a different puzzle and it's still a character-based puzzle, but you know, you gradually teach them what the vocabulary is. And so there's never a situation where you see the character generating a scripted line that uses a construction that the generative ML system doesn't understand, and so they like go off on some tangent trying to talk to the system about something it doesn't understand at all. Yeah.
Thank you.
And last question.
Very important category of costs. I really like how you positioned the set of people's assumptions and the AI that was assumptive. Were there any opportunity to experiment with shrinking the base assumption in the sense that not necessarily placing it in a white middle-income American white household, but rather, 14th century Ottoman colony on Mars? We all know and have assumptions.
What I should have done and thought about and didn't and just should have done was to say, you crash landed on an alien planet run by robots. And so there are not, you don't have expectations, and in fact, maybe you even start out, part of the gameplay is figuring out what their weird language is. That would have helped with the cultural problems.
Come back from hiatus.
Yeah, but first I have to deal with the things that have been distracting me since then, and I'll talk about those later.
Thank the speaker again. Right, so the next up is going to be After automated design via conceptual design.
Thanks. Hey, yes, I'm Nico Sal, from Tech, for my advisor, developed. And this is work entitled, automated game design via conceptual extension. We'll get into what that means in just a second. So there's been a lot of sort of prior work on automated game design. It's almost all had distinct motivations about why we might want it. Things like cutting costs in game development, things like democratizing game development, or allowing for new types of gameplay experiences, or exploring notions of artificial creativity and design. Shout out to my cook. There's been a lot of these prior approaches, not like a massive number, but enough that I can't put them all in one slide, my apologies. But these approaches have typically used procedural content generation. And if you're not familiar, procedural content generation works by having a human designer input their design knowledge into an algorithm. And an algorithm is then used to generate that content depending on what kinds of design knowledge we get. So it could be things like game structure, stories, quests, art assets, etc. So for most of these automated game generation approaches, they just sort of are generating rules or generating rules in levels, and that's the game. That's how it works. But there's some fallbacks to traditional PCG. It tends to require a design expert. It also requires a CS expert. If you're lucky, those people are the same person. Otherwise, they have to communicate, and that's a whole thing. There's encoding time in terms of actually getting the design knowledge into the algorithm. And then design iterations are costly. And there's work on all of this, but these are some fallbacks. So what if we could automatically encode the expert design knowledge, say through machine learning? Well, unfortunately, there's not just like an easy, pithy example here of like, oh, of course, we'll just throw machine learning at it and it works. Machine learning has its own challenges when it comes to game generation. So typical machine learning requires some common representation. And this is tough when we're talking about games, which are just pieces of software that vary hugely in terms of what entity are involved, what kind of logic is involved, etc. Second problem, typical machine learning approaches can only produce outputs similar to their input. And that's good when we're trying to generate images of cats. We don't want an image of a dog, we want images of cats. But it's not great if we want novel games. So what do we do? Well, here's the top. The first bit is we're going to talk about that representation learning. We're going to learn a new representation, get that design knowledge. And the second is how we go about producing novel output. So let me walk you through our approach for learning our representation games. We're going to assume that somewhere out there's an author game engine in levels. So somewhere there's all of the rules and levels of the game, but we're never going to see it. It's a black box. That produces output gameplay video along with a person playing that game. And that's going to be where we're actually going to get stuff from. That's our input. From this gameplay video, we are going to learn a model of level design and a model of the game engine, so all the rules and mechanics. Then we're going to combine those together, and that's going to be our representation. That's what we're going to learn. At this point, if you haven't seen another talk that I've given, you might be saying, well, I use video. And if you have seen a talk that I've given, you've seen this slide before. Well, video has these benefits. Existing corpora games are not always available. It's technically not legal for me to have ROMs of games on my laptop, and I definitely don't. Also, games contain player game element interactions, and that's huge. If I just have a piece of software, I don't know how a person goes about playing and interacting with the software. And they have everything needed to fully recreate a game, or at least that's what I'm going to try to pitch it on. So that was that's our pitch for using gameplay video. Now let's look at this representation. So when we're parsing video, how we do it is we have the initial video that's on your left, and we take OpenCV, which is this open source computer vision toolkit. I'm not a computer vision researcher, and a sprite sheet. And the sprite sheet just contains all of the elements of the game, everything that could possibly be in the game. And we're going to parse that out, and we're going to get the sort of middle gift there, which is a sort of representation where we have what images are where on screen for each frame. So that's our actual representation. That sort of gives us what's going on in each frame of each video. So then in terms of learning the level design, we use a model that looks a little bit like this. Unfortunately, I don't have the time to walk you all the way through it. But you can check out the game level generation from gameplay video paper where we actually talk about this thing. But generally what we're getting is sort of the shape-to-shape probability relationship. So like, what's the probability of seeing, say, this thing at this distance, this relative location to this thing? This sort of representation. And then we can use this to string pieces together to be able to create whole levels. We can also use it to evaluate. It turns out that it correlates really strongly with human measures of game design or game level design.
Okay, so that was level design. Now let's talk about this game engine. I'm going to talk about this a little bit more because it's a little bit more complicated. So this is generally our rule learning system. If you want all the data on this, you can check out, oh, that's covering it. It'll stop moving and it'll work. You can check our AIIDE paper from 2017, Game Engine Learning from Video. So what this does is we extract what we call facts per frame from the game. We then scan through the sequences of frames representing these fact representation. When we cannot correctly predict the next frame, we're going to use something we call engine search. So in terms of the facts, this is sort of like formal logic facts or percepts. So we have a certain number of fact types, like animation, which is what state is each thing in terms of the sprite sheet. Spatial, where are things on screen. Relationship x and y, it's the distances in x and the y dimension between things. Velocity x and y are hopefully straightforward, and camera x is how far we are to the level. So if I were to take this frame of Super Mario Brothers, I could represent it out with these facts, and so on and so forth. This is a very dense representation. Then when we're scanning through the frames, it works like we have two pairs of frames, two frames next to each other. And for the current frame, we pass that through our current engine, and that predicts out what it thinks the next frame is going to look like. Now, it could be wrong, as in this case. And if that's the case, then we need to do engine search. It's worth noting here that we don't author any rules initially. So the empty game engine at the start is just going to predict whatever it's given. Engine search works a little bit like this. Basically, we're just going to create every possible permutation on the current engine. That's by adding all possible rules, modifying all possible rules, deleting all possible rules. The rules that are added are just proposed from the facts in each frame. Again, there's no templating here. And we're then going to select the next current engine according to performance and parsimony, and you jump back to the start every time just to make sure we didn't break something. And you train this thing on a couple videos of gameplay videos, say for Mega Dance or Mario Brothers, and it's something like this. So this is on the right as the true video, and on the left is the sort of predicted video from the system. And it turns out that we beat out deep learning approaches with the same amount of input data, and we can use the same sort of learned game engine to predict, to teach a game playing agent as well as the true agent, the true level. Sorry, it's early. All right, so that was the learning the game engine. We got that down. Now we need the combined representation. And that's going to be something we call a game graph. So I'll talk about how we put that together real quick. So game graph generation works a little like this. Remember the sprite sheet from earlier? That and now each entity in that sprite sheet, each image is going to be a node. So this is the initial game graph, just this over here, totally unconnected, all these nodes just floating in space. Then we're going to grab edges from our level design and our rule information, and we're going to use those to connect up all the nodes. So it looks something like this. This is a tiny simplification of the Super Mario Brothers game graph, but I can just like give you a sense of what's going on here. So like there's this relationship Y, rule condition edge right here between this Mario node and this Uma node. There's an animation edge here connecting that this node can become this node, et cetera, et cetera. Okay, so there we can get games. We can get this representation of games. And it's pretty decent. But now we actually want something new. So how do we do that? So again, the typical machine learning approach might be something like learn a distribution over our game graph representation, then sample from that distribution. But if we do that, then we get this problem that I mentioned earlier of getting output only similar to our input. And that's not great. We'd like something new and interesting. So we're going to turn to an approach called combinational creativity. Now this approach, there's a large area of research, and I don't have the time to go over it fully, but essentially it's the kind of creativity that you or I use in order to recombine existing knowledge to make something new. So we'll do just a brief example, going over for two inputs what the output of conceptual blending is, which is perhaps the most popular of these approaches. So for the input, resident lives in a house on land, which is sort of a graph representing the idea, the concept of living in a house, and passenger rides on a boat on water, which is again sort of the concept of riding a boat in the water. Conceptual blending would give us a resident passenger who rides or lives in a houseboat on the water. So it sort of invented the notion of a houseboat from those two inputs. And that's one particular output of this algorithm. You could have others. So generally, it's the case that you only want two inputs and a single output. We can sort of imagine the space as possible combinations with something like this. So let's say we had Mario and Kirby. If that was the case, every single point in this space, every point in this graph, would be a potential new game graph, a potential new game. If we use something like the amalgams from the previous slide, we might get a sort of interpolation between the two games. If we use conceptual blending, we do like an extrapolation, and compositional adaptation could give us a change in model complexity. So a change in like the complexity of the game. But what if I want to game over here, or over here, or over here, or over here? And what if, even worse, I have 3 inputs? None of these approaches handle that. And they also don't handle numeric data, which game graphs have a lot of. So that's an issue. But if these are all points in space, you can think that there's a function we could define that could represent each point in that space. And that's what we made. So this is conceptual expansion, which is a novel combinational creativity approach. And it is just represented by this function. Let me walk you through it real quick. So the F values are the set of all mapped features, e.g. the edges of the game graph. The A values here are the set of filters. These determine where, what pieces we're going to grab from each of our filters in terms of features, hopefully features, what pieces we're going to grab from our features into our final game graph. And then next is the concept we are attempting to approximate or create. So like a simple example here, we just like pixel emoji. We have these 3 input, these 3 sort of bases, and we can use these A values, these filters to determine what we're grabbing to make something new. So for this, for using these game graphs, what we're going to do is we're going to take input, we're going to take from our input game graphs, we're going to map all the features onto one another, basically doing categorization. That gives us F values. Based on the initial sort of distances of these categories, we're going to get our initial filters. That gives us A values. And then we're just going to optimize F and A for hill climbing, given some heuristic to approximate X, where X is maybe a new game or a particular game we're trying to reapproximate, things like that. And as a heuristic, if you use like playability and novelty, meaning it's something entirely new, you can get something like this thing. So here's a video of me playing a generated game with this approach. All of the rules and all of the game structure is created by this approach. I made the visuals, which is basically just me picking colors that the rectangles are going to be as I provide the system. And it's kind of interesting. There's some interesting stuff going on. I showed this to Mike Cook, and he asked if the input was Mario and Brick Breaker. And you might think that naively, but no, the input was what I showed before of Mario, Mega Man, and Kirby. So what's happened is sort of combined notions of game structure, like the ground blocks and blocks in general, with notions of like enemies from Mario in terms of disappearing on hits. So there's this interesting thing going on here. And there's other videos like this you can find on YouTube and stuff. So, question, how the heck do we evaluate this thing? What we ended up going with was a 3-fold cross-validation. So we're going to try to recreate Mario, Kirby, or Mega Man, given the other 2 and partial information on that desired game. So let me go a little bit more in depth on that. So what's essentially going to happen here is we're going to have training and test error. So we're basically saying, given a goal level design, make me a whole game, both rules and level design, that sort of matches that. So then the level design in this case would be the training error, and rule design is the test error. Okay, and then we're going to do vice versa. So given the rules as like a feedback mechanism is the heuristic, that's the training error, then the level design information would be the test error. Okay, so we created some, I know. So we made some baselines, conceptual blending, which is the most common of these combinational creativity approaches, KNN, which is the closest to the 2, and a GA. Notably, this GA is just an optimization approach, and so this is primarily a change in representation. And generally, I don't have the time to go over these fully, but conceptual expansion does like significantly better than all these other approaches. There's one little point out here, which I'm happy to talk about some other way, we have in the paper. But we do very well sort of recreating these games, which is very exciting. So some quick future work. We want to handle the other bits of games that we're currently ignoring, like story and visuals. We need to do a qualitative evaluation, explore different types of games with input set, and get this in the hands of novice and expert designers, because that's when we think it's like really cool. We can really do some cool stuff. Some quick takeaways: we can apply conceptual expansion to recombine machine representations of game levels and rules, and this approach outperforms existing prior approaches when recreating old games. And I promise I'm finishing. The first machine learning-based automated game designer, as we think it is. If you think we're not, please let us know so we can correct that. All right, thanks for listening. Thanks. Yeah, any questions? Adam, yeah.
So you said video gives you everything that you need, but you don't actually have inputs. So how do you inject those back in?
Have you read the HTech paper? No, so
Well, I know how you incorporated with the engine learning, or that you have the possibility for input, but like something right doesn't make your thing go right unless you, as the human active.
That's a good point. So
Matthew,
there's
can you repeat for the stream, please?
Yes, can repeat the stream. So basically, how do you get inputs produced and generated out of games? How do you basically pick the key bindings? So we just have like custom key bindings for the different rules. So I picked, for example, that okay, I'm gonna hit the right button for this particular rule, but it's just set up on the per rule that's actually a control rule or like a player rule type thing. So I can pick whatever key binding I want as the player. Yeah, Julian.
So I really found your example compelling where I think, like Mike, I assumed that it was Mario plus Cricket.
Mm-hmm.
Is that because core mechanics are not actually ever captured, and so all mechanics could equally be core? And are there other places where something like that happened where it maybe wasn't as interesting or compelling in your results?
Sure. So lots of times. It's produced games where there's a power up that you can never reach because anytime the player gets within a certain X range, it moves to the right. It's made lots of bad stuff too, and the current work is really on okay, how do we make sure that it's producing good stuff mostly. Yeah, go for it.
So learning from video is really a cool idea, but I'm wondering how general this is for different camera models. Here the examples you showed is 2D games with camera directly aimed at the level. I'm wondering if there's 3D levels or maybe some is first person. Do you think using some more advanced computer vision, this would just conceptualize your work, or?
Yeah. So the question is basically, what about 3D? It's a common question that I've gotten. So as I mentioned at the top, I'm not a computer vision researcher. I have talked to computer vision researchers, and 3D would be possible. It's also the case that these approaches, specifically the level design style approach, was actually originally created for 3D. So I have every expectation we could do it. It's just that I don't care about the vision problem.
Okay, thank you.
We have time for one final quick question.
So it's learning from video, but there is this really important caveat that you're turning that video into placements of tiles from the sprite sheet, right? So that's where you learn on it.
Sure.
So have you just done it from pixels to try?
So this entire approach depends on the fact that we have a component-based information. So we have to have information per each sprite. And so from pixels would not work super well. We have to redo a lot. All right, thank you all.
Yeah, thanks.
All right, so the next talk will be a mini version by Chris Martins and Alan Sorrell on Gemini, bidirectional vision analysis of AIIDE.
Thank you. Hello, everybody. I'm Chris Martins, and this is Alan Sorrell. We're going to be co-giving this talk on Gemini, and this is work that I did as part of my postdoc at UC Santa Cruz with a whole bunch of great people there. This is on the slide, and we're going to be on work on this, so happy to be presenting there. So we are also talking about this problem of automated game design, one introduced by Matthew in the previous talk, and are very much inspired by work with Clifton and Trainer on this problem of basically how to generate novel games that are somehow interesting to play in some way. The approach that we take is one that really has more to do with kind of a theory of meaning, right? Sort of how we come up with a relationship between a game and what it means, in a similar way to kind of media studies, right? When you watch a movie or read a book, what kinds of practices do you use to understand what the meaning is behind sort of what the designer was trying to do when they made certain design decisions? And so we take a bi-directional approach here. So we have a procedure, basically a logic program that tries to extract, go from meaning to game in order to generate games. And to do that, we need to first be able to reason from games to meaning. So we have this bi-directional process that works together, thus the name Gemini. So Gemini consists of two pieces, Castor and Castor is the piece that derives meaning from getting rules, and Gemini is the piece that derives rules to match meaning. And our talk is going to proceed in the same structure, so I will be talking about the Castor system, and then I'll pass it over to Adam. So I want to show you a brief video of the game, a little bit of gameplay of the Free Culture game, which is an indie game made by the Hello team. This uses the term the game name of the Industria to describe his game studio. Oh, actually, I'm going to go. Yeah, so it walks you through a little bit of verbal instructions, explaining kind of how the game works, what the different pieces of it are, and the metaphor that it's trying to communicate through this game. So there's these little people that are green, they turn to gray, and they flip over into the consumers area, and their mission is to liberate them by spreading ideas throughout the audience. So this is a little bit of a gameplay. So you just have this cursor, and you kind of push the little light towards the green people to try to keep them green, keep them fading out, and looking at the other side. And this little character around the rim is going to come around and suck up all the great light-bulb ideas and go around and distribute them to all of the consumers on the outside of the circle. Okay, so this is a game, you can kind of use it about what this game is about, given the verbiage that was given in the beginning and some mechanics that you see. So the theory that we are relying on to kind of understand a game like this is really the sage difficulty of Bogos. Is the idea of proceduralist readings, where it's broken down mechanics, the types of interactions that are possible, as well as the cultural meaning that we imbue into things like the visual representation on the screen to derive some kind of deeper meaning about capitalism and distribution and intellectual property. So the framework that we have for this kind of starts with game definitions, things like rules and mechanics. From that, we can extrapolate into dynamics. If you remember your MBA, you read from game design, which has to do with the emergent behaviors that result from the interaction between mechanics and players. And from there, we can sort of use thematic and culturally associated elements to extract aesthetics. All of these things together combine to form meaning, combine to form something that means something that has a reflection on the external world that we use to develop this kind of reading. Right, and then there's this big bubble that we just, kind of draw a circle around right now for this work that we call culture, which is encompassing all of these different pieces. Okay, so we have a, what time did we start?
Can I start at 10?
Okay, great. Okay, so we start with, start by describing some definitions, right? So we're basically encoding this whole structure of deriving meaning through the MBA process as a whole program. So we start with some basic facts, which describe what types of things are keys and resources in the game. We can describe some mechanics using syntax embedded in prologue for describing basically rules in terms of their preconditions and effects, like things like there might be a control event, which is a player input where they're holding the up arrow, and in that event, we activate the mechanic move up. So move up is just an uninterpreted symbol in this representation, and we give it some additional meaning through this result rule, which says that a result of the move up action is that the paddle moves 1 unit to the north. Okay, so this is a quick sort of example of how Cygnus works. So Cygnus is the domain-specific game representation language that we use in MetaNet and prologue to represent the mechanics of the game. We describe a bunch of different input modalities for this language, including mouse cursors and clicking, key presses, releases, and holds. And rules are arbitrary pairs of preconditions and results that sort of come from different subsets of the types of things that we can infer within these input mechanisms and other sort of mechanical units. So we have arbitrary sort of behaviors and resource flows, as opposed to we allow the authors some flexibility in terms of how to author the space of possible game mechanics, rather than just saying, there's a fixed pool of things like something collides or like a gun fires or something, right? Like that lot of existing game description languages have just a large library of fixed definitions for it. And the other thing this lets us do is that when we have sort of structural representation of the game mechanics, we now have a semantic. We can extract semantics from these rules and use it in our code. So, for example, if we want to know what kinds of entities the player controls in the game, we can give some rules to define that. So we can say a player controls some entity X in the event that there's a precondition where there's a control event that has some outcome, and the result of that outcome is that the entity X moves in some particular way, right? So if you put this in sort of a zoom out level, this is saying that if there's some control event that moves the entity, then in fact that entity is player controlled. So this is just an example. We instantiate these particular terms to allow us to infer that the player controls the left paddle in, for example, a game of Pong. Additionally, you can infer that the player controls spaceship and something like that in a similar manner. So this is just to remind you of this when we're talking about the free culture game. So if we want to try to figure out what is the player trying to do in the free culture game, which is sort of an instance of a dynamic, something that we have to infer from what the player's goals are, what the types of control they have on. They can push around these little light bulbs, and sort of the other things that are happening in the game, the dynamic consequences of those rules. We can build this whole tree. And I always want you to read this to be able to see the text in this bubble. But the point here, is essentially that this is a constructed argument tree that you can extract from the logical rules of prologue, which takes the exact structure of the procedural history game, which says that we can reason from these green nodes, which are the mechanics, through the rules, which are the red nodes, to certain things, which are the orange nodes. And so within each of these levels is some actual protocol code that we use to do this kind of static analysis reasoning over the shapes of the mechanics of the game. And with that, I will turn this over to Adam to talk to you about how this structural analysis is generated.
Thank you. Yes, so this is all for the purpose of generating games, and so Chris described the system, which was the first system we built, which was given rules of a game, try to infer all the properties about the game. But so Pollux is working in conjunction with the system, and in fact sort of simultaneously with the system. It's not like Pollux does something, and then Castor goes back and says the meaning, and then Pollux makes refinements. This is working via answer set programming, and so it's trying to find a stable model of a game with all of these things operating all at once. But so the general goal was that, given a high-level design intent, so a designer of a game has some, types of things they want the game to be about. We want to generate games that match that. So these might be sort of relatively simple things about the dynamics, like it's a game that requires hand-eye coordination, or it might be something, about the resource flows, like you might try to maintain something, or other things, like it might be a game that should be calm or threatening, and so higher level meanings that we might want to derive from that. And so, as Chris mentioned, the rules, the way that we represent mechanics in Gemini are via these pairs of preconditions and results. And so, what Gemini does is it is allowed to sort of choose pairs of things that can be in preconditions and results, and that is sort of the soup, primordial soup that it is building up from. So in ASP syntax, these sort of curly braces are things that the system is allowed to choose, and so it's allowed to choose things that can be conditions and preconditions, and then pair those with actions coming from results. And so some conditions that we are looking for are things like control events, or overlapping between entities, or resource thresholds passing certain polarities. And the actions that can result are things moving or rotating, or entities being spawned or removed from the scene, and resources changing in arbitrary ways. So this is what Gemini is sort of allowed to pull from. But it's not doing this just sort of
pulling out a handful of things and throwing them at the wall and having the caster then make refinements. Again, this is all sort of happening all at once. And so it's doing this subject to constraints. So, you know, we might have some simple constraints like there shouldn't be an action that decreases a resource by the value of that resource, because that's just sort of a weird way of setting something to 0. And so this is sort of just a sort of meaningless semantics that's already being covered elsewhere. Or we might not want an outcome that is unreachable, where unreachable is obviously one of these properties that is then being inferred from the rules. Like, you know, something might be unreachable if it involves moving an entity that would require an entity to overlap something else, but there is no way to ever move that entity. And so that's a game that should never exist because it relies on a mechanic that isn't present. Or that you might not want to have an outcome that doesn't rely on any precondition, because again, that outcome could never fire. And so then there's all of these sort of common sense rules. I think at last count around 280 common sense rules that sort of preclude, or that sort of prune away the space of games that are just sort of nonsensical and meaningless and unplayable. But again, this is all trying to satisfy a design intent. So for instance, one of the design intents we had for an experience we were building was a game that involves hand-eye coordination. It should, the player's action should have risk and reward. There should be a bad resource called maintenance. The player should be able to lose the game, and then the computer has some entity that they can control. And these would be encoded in these ASP rules in this way. I'm not going to get into it. But then these are then reified in different games. So here's one such example of a game where the player is controlling this sort of red triangle, and wherever they move it, it erases these sort of blue trails. And if the blue trails get too high, then they lose the game. And simultaneously, there are these yellow things that are sort of threatening to the player, where they are producing these trails that are bad, and can also destroy the only means that the player has to combat this sort of growing threat to the game. And another game that is sort of almost exactly similar, or came from the same intent, but has very sort of different mechanics. Here the player is again sort of controlling these red triangles, but instead of dragging them along, they are causing them to sort of rotate and trying to have them avoid these yellow threatening triangles that are constantly chasing them. So the same intent can lead to sort of pretty different games. And all of this is to support an experience. Emma's Journey, please check it out. I'll have the URL at the end. But it's so a procedural generator for games paired with a procedural narrative generator, which is well beyond the scope of this talk since I have about 15 seconds left. But you know, check that out later on. Other people write about that. So in conclusion, Gemini is a system that is both able to infer meaning and aesthetics and dynamics from the rules of the games in this language Cygnus, and is able to use this to generate games that match a specific intent or have specific properties. And again, all of this was to support Emma's Journey. So thank you. And I should mention this was supported by questions.
Technical questions? Yes.
Very interesting. I was interested in the design events.
This one or this one?
I meant to repeat the question before.
Sorry, they were interested in design intents and wanted to see the slide. So, not the question so far, but maybe coming.
If you can go over the next one?
Yes.
Those and explain what they do,
yeah, so we have these sort of pool of readings that we authored. So there are things, constructs in the language that are things like reading. We might have readings of a hand-eye coordination, and that's about the game on the whole. So we can have design intents that are about, you know, properties of the game, such as design, you know, hand-eye coordination, or that it should be relaxed, or that it should feel frantic, things like that. Which are then inferred via the properties of the rules. And what this means is that there should not, like, the headless rules in ASP mean don't let this thing happen. The not after that means essentially do let this thing happen. So it must be the case that there is a reading about hand-eye coordination in the game. Or something like, there must be risk and reward to some control event. So the way that the player is interacting with the game must carry with it some risk and reward, which again is going to be inferred by a series of rules that build up and try to infer whether there is a risk and reward. Some things about there must be a good resource, there must be maintenance of a resource, the game must be able to be lost. Games can be lost, some games can't be lost, some games can be won, some games can't be won, etc. And things like, again, there must be something entity that the computer is also controlling. I don't know who was first. Ian, I think was first.
I'm sorry. I keep thinking I understand ASP and then discovering there's subtlety on
That is correct. Yes. ASP is not able to be understood.
What's the difference between turnstile not reading and simply saying reading?
Yeah, yes, I work in this question. So what is the difference between saying turnstile not reading, colon dash, grants turnstile, turnstile not A, and just A, right? Okay, so great question. So ASP lets you establish these things called constraints, which are, or integrity constraints, as Adam mentioned, is kind of a way of ruling something out. So when you just say, let me take a particular example, like,
Yeah,
say,
reading and coordination.
well, let me talk about that. Let me say, there exists or the reading where there's a good resource, right? Like, if you want to just say there is a resource that is good, if you were just to state that as a fact to ASP, it would then, kind of say, okay, you've given me a new way to make a resource that's good, and so you're essentially giving it a new way to kind of add something to the game. When you instead say, I would like you to not give me any games that lack a good resource, what it's going to do is it's going to use existing facilities for adding good resources to the game, and then eliminating the ones that don't have a good one.
So you're saying it has to be provable that there is.
Yeah. If you just said reading good resource, then it would just say like, okay, well, thank you for decreeing that. Like you now everything that you produce is happening. By fiat, you have made this true. Not you. We are forcing the system to prove that this is true.
So we have time for one last question.
I have a question. My experience with ASP, which I think is similar to Ian's in that, like, I don't understand.
Also correct.
It's like shockingly easy to make it so that everything blows up, right? So were there any things that you intentionally did to try to make this a tractable, solvable problem, or like areas that you ran into that you would caution people about?
So we could talk. So the question was, ASP has a tendency to blow up in sort of the combinatorial space that it's searching through as part of constraint solving. And were there any sort of sweet tips and tricks that we might offer? And I can go on for hours about that. So a lot of it we're trying to prune away the things like complexity that would blow up the state space, but were completely meaningless to us. Like, right, for the games we showed, right, like it involved red triangles and yellow triangles. Like we specified, well, the first thing that, like the first entity that's generated will always be a red triangle. Because at this point we didn't care about like theming it and coloring it and change and stuff. Like, we could add that in, but for this, it's just like, okay, we're just going to make sure the first thing's a red triangle, the second is a yellow triangle, etc. in all the games. Because that wasn't the thing that was being sort of reasoned about at the time. So things where we allowed it to choose from any shape or image or that would blow up the space, but it might just randomly pick something and that isn't being reasoned about. So that was sort of meaningless complexity being added to the space. So a lot of ways to prune it, essentially, like you shouldn't have a seventh rule without having rules 1 through 6 or something, right? And because it might kind of permute the rules in different ways or have different combinations of them that don't actually result in different play of the game or something. So ways of trying to limit what is the complexity while still being able to reason about things that are interesting and meaningful.
Thank you.
just wanted to add, I just wanted to add, consulting with, like actually doing a consulting session with how this work happens. Walking through something like this was really fun.
Also does not seem fully tractable, but okay.
Yeah, we need to scale out this one.
Yes, thanks.
All right, so the next speaker is going to be Anita Sturman, and he's going to talk about exhaustive and semi-exhaustive procedural. Thank you. So this is work that I did with Matthias Sosa, and he was a visiting undergraduate from Brazil who wanted to become working in my lab when I was formerly at the University of Denver, and now moved to the University of Alberta, so I'm across the hall from now, across the quad. And this work, I've talked about it in sort of smaller venues before, and part of the motivation for writing this paper was looking at this PCG book that was recently written, and I just sort of taking through some of the ideas that are in here and showing where I felt like there was a gap, and not only that, I had people coming to me and saying, I'm interested in this, but I don't quite know how to do it. And so I wanted to give some tips, sort of write this sort of high-level overview paper that gives some ideas on how to do that. In this talk, I'm going to try and motivate how would you use a system like this? So I'm not going to try and get into the mathematical details, but more talking about high-level design issues. So some taxonomies here, we have constructive PCG grammars and other things like this. And then there's this section on search-based PCG. And search-based PCG is then split up into evolutionary algorithms, where there's some time spent there in the book, and then there's sort of everything else. Everything else includes very brief mentions of exhaustive search and random search, and then there is a section on ASP, so thank you, Adam. And so the system here though on exhaustive search really doesn't go into detail about how you do this, or what type of things it enable you to do. And so that's what I wanted to talk about today. The paper is doing some synthesis of some of the mathematics of other fields. As I said, I'm not going to go into a lot of details about the exact mathematics here. I am going to give some examples of some algorithms just to give you a flavor of the type of things that can be done. And then we're going to talk about, I really want to give you a sense of what are ways that you might want to use this. And this is very a mixed initiative process where it's really a conversation between me and the solver that's allowing me to generate content for puzzles, in particular really with puzzles and games. And I'm going to focus primarily on a game called The Witness here, because I think this is sort of the most interesting content that we've generated. And I'm going to have to spoil some of the puzzles if you haven't played this, but it's been out long enough that if you're a puzzle, aficionado or play it, then that's your loss. But if we look at these puzzles, so I'm going to give you a sense, like you don't have to understand exactly what's going on here, but I want to give you a sense so you're going to understand what the system is doing. And so we have puzzles like this, and there's sort of two things that are going on in this puzzle. So one thing that's going on here is that we have to draw a path. So here's a path that goes from the start. The start is a circle in the lower left-hand corner, and the goal is this little notch that comes out in the upper right-hand corner. And so there's this constraints on the types of paths we can have. These are technically called self-avoiding walks. So this first one is valid, here's another valid path. But this isn't a valid path because it didn't avoid itself. So that's the requirement on path. So there's some requirement in any path that you use in the game has to follow the constraints of self-avoiding walks. And then the second thing is that we have these yellow pieces here. And these yellow pieces are additional constraints on the path. And basically the whole game is about developing different constraints and showing how they can be put together in different ways. And what these yellow constraints mean is they mean that when I trace a path, I basically have to follow these constraints. What I do is I'm actually solving like a rectangle packing problem or a shape packing problem, where I take these pieces and I virtually lay them out on the board. So I'm going to blow this up, I blow this piece up, and I blow this piece up, and then I say, now what you need to do is you need to trace around this shape so that there's a line that exactly outlines the shape that you've built virtually here. And in particular, these spaces here should not be part of the shape. So it has to be a tight sort of shape covering of the pieces. And so there's no way I can actually draw a line from the start to the goal here that actually cuts out these two black regions. So this wouldn't be a valid solution to the puzzle. I can do things like move the pieces around. And again, I can't sort of draw a path that cuts out the inside here. So I can't do that. But I could move the pieces around like this, and then I can come up with a path like this. And so this would be a valid solution to this puzzle. And the thing here is that I don't actually lay out these pieces in the puzzle. I do it in my mind, and then I draw the path to show that I understand these constraints within the problem. So this is the game. This is the puzzle that exists in the game. I'll come back to it and talk about that. But when I had to start working on this problem, we said, let's try and create some new type of puzzle that wasn't explored in the game, but we're going to sort of riff off some of the things that are there. I said, let's take 3 puzzles, and we're going to try and find one path that solves all 3 of them simultaneously. And the way that we looked at this is sort of inspired by secret sharing algorithms. And the idea is that if I give you any one puzzle or any pair of puzzles, that it won't give me any information about the final solution. So the idea is I give you a first puzzle here, you can think of many different ways to solve this. I can give you a second puzzle, there's many ways to solve it. A third puzzle, there's many ways to solve it. But when I put all 3 together, now boom, I can solve them all, and there's actually one solution to all 3 puzzles joined together. And so it's a slightly different reasoning task than you saw. There were some puzzles like this in the game, but they didn't explore this aspect of it. But one thing we did, so this is part of the conversation, and I'll sort of get into the mechanics behind this in a minute, is we noticed that when we generated these puzzles, that all of these puzzles, the pieces tended to be in the same area. The constraints here in the same area of the puzzle. And what it meant is that you can just reason out those ranks squared, and then you can say, yeah, well, if I reason about that, and I just do a little bit of extra reasoning on top of it, then I can very easily solve these puzzles. And so then we went to the system and said, okay, well, don't do this. Give me puzzles that this property doesn't exist. And he gave us new puzzles that look like this, and I'll give you the URL if you want to go play with these later, but basically we started showing them to people. In fact, there was a bug in the program that generated unsolvable puzzles the week before, and then when I got the first one of these puzzles, they said, oh, there's got to be a bug in the program still, because I can't solve this puzzle. And it ended up that actually the puzzle is solvable, and what it's doing is something that's very desirable in puzzle games. It's actually my mental model wasn't quite right, and I had to break my mental model and learn something new. And so what we found is that this process was able to do this for me somewhat automatically. And so I think we found this to be a great tool for sort of exploring game design and having it teach us about the game design without us having to figure out everything ourselves. Or gave us new puzzles, and even we as designers, sort of this set of puzzles, found unexpected things in the puzzles that were generated. Okay, so getting back to the BCG, exhaustive BCG, as we define it in the paper, would be approaches for generating content where we're going to look at all possible content by some methodical method. Okay, so we're going to look through all of it, and a random method would look at all content eventually. So I don't really like random methods being exhaustive. I really want the idea that we're somehow exhaustively looking for it. In practice, of course, we have very often be semi-exhaustive. That is, I have the potential to generate everything, but I'm actually going to do some pruning so that I can make the problem more tractable, because many problems can be too large. And to do this, there's 2 things we need. One, we need some sort of evaluation. It's going to evaluate the utility of a given state, so I can select the content that has the highest evaluation. And then you need some sort of generator that can enumerate states. And actually, I did point this out in the paper. We can do generations by analyzing permutations, combinations, things like multi-sets. And there's very nice mathematical properties on those, and that's where the paper is sort of focusing on. But if you look at something like ASP or SAS solvers or constraint programming, they're doing sort of recursive handling of variables and values. And so you can handle it, we can do BCG sort of in both ways, but there's a lot of things that you can do if you can actually enumerate the combinations and permutations, because it allows you to store them all or store them in a very compact way and do computations. Well, I'll show you an example of one of them in a minute. And so I'm focusing a little bit more on those than sort of just generic recursing over variables and the values of those variables. So if we're thinking about these mathematical functions, there's 2 things we're often asking for, which is something like a max rank, which tells me basically how much content is there in a particular puzzle. And then I have 2 functions, one that takes a state and ranks it into a hash function. So that's going to give me basically a numerical value, and it's going to range from 0 to max rank, or max rank minus 1. Actually, it's a bug on the next slide, so I've got to put minus 1 in. And then an unranking function takes a hash value and gives me back a state. And so this way that I can sort of index all the content, and I can map back and forth between numerical values that I can handle very well, like for loops and actual states that I want to reason about. So I'm going to do 3 examples of how we can do this and the types of things that you might do. And there's sort of many other things that you can do, sort of depending on the problem that you're actually trying to solve. So if I go back to this board we were looking at before, and we say, I have a lot of different ways that I can design a particular puzzle on here. For this particular design, I'm going to say, well, look, this is a 4x4 board. So for the constraints we were looking at before, there's 16 locations that I can put these constraints in. And the puzzle before had 3 pieces in it, so let's just say there's 3 pieces. And then I'm going to have a library. This library has 11 piece types that I can choose from. And so the mathematics of this is just that, well, there's 16 choose 3 sets of locations that I can put pieces on the board. And then each of those pieces can be one of 11 types, so it's 11 to the power of 3. We're allowed to repeat those types, so that's fine. That's why you 11 to 3. And there's actually 750,000 ways that you could build this sort of puzzle. And 750,000 is hard, it's a big number for me if that was dollars or something like that. But for a computer, this is usually less than a second computation. So this is something that my computer could run through, and we could do this exhaustively. And really, with very little optimization in the code, to get something like this to work. And so what this would look like is something like this. So from 0 to max range, this should be -1. I forgot to fix that. And then I would just say for each integer, I'm ranking, so I'm going to take it from the numerical value into a state. And then I'm going to calculate the evaluation of that particular state. And then if that's better than the global evaluation I have so far, then I'll update what my best evaluation is. And so if I have that, then the question is, well, what evaluation function do I want? And actually, if you look at this puzzle here, so this is one that's available on the Witnesses webpage that they put out as one of their special puzzles. And if you look at this, what they're doing is they're actually taking these pieces, and the virtual location that the pieces are put are about as far as they can be from the actual location of the pieces on the board. And so what I think, this is just my guess, is what I think is going on here is that the choice that was humanly designed was to say, I really want to train the user that the pieces themselves in the virtual puzzle don't have to be on top of their low-level constraints. And so if we put that constraint into, we run the solver, this is the type of example we come out with. So we can sort of say, I want this content, what happens? So this is what we did for this particular puzzle. We had 9 locations, we had 3 pieces and 12 piece types. And so that says there's 150,000 ways I can do this. But remember, I want 3 puzzles. So I actually have 150,000 for the first one, 150,000 for the second one, and 150,000 for the third one. So this means I've got 10 to the 15th ways that I can design this puzzle. And I don't really want to generate all of these. I might be able to use a computer to do that. But this is where semi-exhaustive comes in. And the idea here is that I can use some sort of branching down procedure to prune suboptimal solutions. I'm not going to go into the exact pseudocode here, but some of the ideas here is we're going to look at single boards. If a single board doesn't have very many solutions, so generally, if we're doing a single board, we want it to have only one solution, but now we want many solutions. So we're going to get rid of the boards that have too few solutions. We're going to look at pairs of boards that have too few solutions, and then we'll exhaustively enumerate the remaining combinations. And once you do this, again, this is a very trivial computation that can be done in a few minutes. And there's some other coding you can do on top of this to make this efficient. And if you want to play these puzzles, they're on movingai.com, so you can go there, and it's a little link on the left-hand side. You can find most of the resources from the talk and some of the links there. One more example I want to talk about is something that I did a workshop for a number of years ago. It's another game called Flame. This is a game where, sorry, the video is just like it, where we roll things into each other and knock them off the board. So we roll into each other and knock them off the board, and so then you're trying to find the pattern of moves that moves all the pieces off the board. This is a very different type of puzzle. What we notice here, so for instance, to put 10 pieces on the board, there's 35 billion combinations. Of those 35 billion combinations, though, very few of those have one solution. Those are the types of puzzles in this particular thing we're looking for. We started late. So
I know, I'm talking about
So it ends up though, because such a small fraction of these boards are actually solvable with a single solution, it means that local search approaches that try and combine together content are not going to work very well, because the content that you're looking for is very, very sparse in the world. The other thing to notice is that if we do forward search, we build a huge forward tree trying to analyze states, and we repeat that tree many, many times. It's actually a real waste because the size of the game is shrinking, and so it means that we're going to repeat analysis on a single state hundreds and hundreds of times. And so this is where we want to use a retrograde analysis approach. And so retrograde analysis is basically saying go through all states, I think -1 here. We unrank a state, that's how I'm going to get the state out, and then I'm going to look at all of the successors. I rank the successors, and then I do some processing to say, what is the property do I want? Does the state have the property that I want? And if it does, then I'll mark that in the parent tree. So this is the way that we can very efficiently build up information that we can then store for doing later analysis. And once we've done that, then we go back to sort of the exhaustive analysis of the states that meet the properties that I actually want. Okay, so final takeaways. There's a lot of puzzle problems and other problems as well that can be abstracted into these sort of high-level language, but that's something different. I haven't written that paper yet. Are very easy to analyze, and particularly because these sort of problems, our human capacity to analyze is very limited, so the computers far outstrip us there, so they can analyze these problems for us. And what this sort of EBCG approach is allowing us to do is ask questions about the state space, and the system comes back to us and answers these questions by showing these example puzzles. And so if you want to look at some of the mathematics, you can find that in the paper, and also there's some sample code on the webpage there. So, very good. Thank you.
Have you found any correlation between unique solutions and like puzzle fun with humans? Like you said you like that, but do people other than you like that?
Yeah, so the question is there a correlation between single solutions and puzzle fun? So I'm going to revert to, I guess, so the simple answer is yes, and then there's a more complicated answer. I've put some of these on Twitter, and you can go find where people commented and say, these are really fun, give me a whole thousands of these, I want to play more of them. And so some people at least are having fun. There's another level though, which is Jonathan Blow and Martin Bosch gave a talk at AIIDE about 7 years ago, talking about puzzle design in terms of that the puzzles somehow exist in the universe and we're exploring the universe. And they suggest that we're not actually we shouldn't be looking for fun puzzles. We should be looking for puzzles that somehow illustrate what is going on so that I learn something about the state space. And in some sense, they're saying, if I mess up on the mechanics or all the things that Ian was talking about and having trouble, his design, if you mess up on that, at least I'll teach you something about the nature of the universe. And so there's some idea here that maybe even if people aren't having fun, they at least are learning something about the nature of the universe. So maybe a better answer.
Question in the very back.
Regarding the point you have mentioned that the forward switching concept, can you do it like backwards? I mean, the final state is board with just one data, then just one call. The last one, right?
Yeah, so the question is, can we do this process backwards? Yeah, so in fact, this is what the retrograde analysis is doing. It's solving, maybe I didn't explain that quite clearly enough. It's called all with one, all with two, all with three, and it's all just a one-step process, so we never have to do the backwards switch.
We have time for one more question, and meanwhile, the next speaker can start session.
Heard you mentioned something like secret sharing and
Yeah. So the question was on what do you mean by secret sharing algorithm? The idea there is if I give n people a secret, I want all n people to come together to be able to answer it. So if n minus 1 people come together, they don't know what the secret is. So this is like, if I give you a polynomial and then degree polynomial and I only give you n minus 1 points, then you can't know what the polynomial is unless you have enough points to actually be able to figure out what that is and solve it backwards. So the idea here is that in each of these puzzles, I'm giving you some piece of information that is not enough to solve the entire puzzle, and you need all the pieces of information. You need a subset. So this is an idea of what sort of makes a good puzzle there, is that any subset of the information is not enough for you to solve the problem, but knowing the full piece of full information together. So that's really just an inspiration for that type of puzzle is the motivation for the secret sharing algorithm.
All right, let's take the next.
All right, so the last part of the session is about consulting talk, really by Guru Hanan on base and scope services. So, hi, I'm Rohit Bhutan. This is my doctoral consultation talk. I'm a second year PhD student at NYU. I work with Professor Eugene for years and in England, and I also work with the Honda Research Institute Europe, Sacramento. So, it's going to be my talk about agents for creative cooperative systems. So, first, a quick overview of what we're going to look at. So, a brief introduction of my research goals, then the actual goal statement, some of my research so far, some of the things that I'm currently working on, and the future steps. So, I'll start with some definitions that are useful. They're not the only definition or the best definition, but the ones that approximate the sense that we're using on the project. So, creativity is about generating novel and useful content. And human-computer co-creativity, in turn, is when a human and a visual system interact in a way that results in a creative output. And the motivation behind all that is that many of current human processes, production processes, could be characterized as co-creative processes involving humans and computers, sometimes more than one human or more than one computational system working together to design something novel and useful. And there are many challenges to make that work. If you look at traditional computational systems, they are very rigid, so they don't work well necessarily with a bunch of complexities of the real world, such as incomplete information, ambiguities, such as working with real world data or natural language, changing environments, requirements, etc. Modeling the behavior of other actors to provide a personalized solution for each user, and communication, not necessarily verbal. And these are all good questions for me research, and we've seen some talks addressing most of them from another video today or in exactly the last few days if you have been there. So there has been a lot of work already in co-creativity in game research. Some people who are in the audience, so we talk about Tanaka from Unity for platform level generation, Proposal for physics puzzle games, the Sentient Cat book for real-time strategy maps, and Mario Mario generation math we just presented. And these are all being offered tools that work from outside the game. We could also talk from creativity within the game world. So the first example is Hanabi. There might be some controversy, but we're just solving a game with explicit goals and creativity. Well, I feel quite creative when I play with another human players, but that's debatable. But we can also look at building an actual game artifact inside of Minecraft with other human users and potentially other bots that are helping you build the city that you want. I think that can very easily be characterized as a co-creative effort. So, although most of my work is going to be similar or similar to this, I've also done some work here and I intend to continue doing this kind of in the game co-creativity. So the main research question that we're trying to ask is what kind of game-like interactive systems, be it within the game or for building games, would provide a good environment for us to express this systems and measure the success. And the long-term goal that we've chosen is to materialize the system as a co-creative StarCraft or StarCraft 2 level editor. And why StarCraft? We think there's a reach design to there. There's a lot of research and also a lot of data for playing the game, but not as much as one or other interested in generating content for it automatically. So we think we can improve and do interesting stuff with the environment. So some of my research so far has been, I think the most important for this talk would be the vision paper that I presented at CIG, where it's kind of a consolidation of my early literature review. So we identified these challenges for co-creative systems. We made a survey of the relevant definitions, the metrics of how creativity is defined and measured, novelty, value, all these related concepts we discussed in there. And we are making an argument for use as a platform for creativity research. I also worked a bit on making agents for Hanabi, which I talked about. Hanabi is a very interesting game. I don't have time to explain it fully, but the main idea is that you play with a hand of cards that you don't see, and you have to play them in the correct order to the board and give hints that are limited in both number and scope. So there's a bunch of like guessing going on, player modeling going on, like how many this, but he doesn't have the full information. Will we go ahead and take the risk and play a card? Or will we wait for me to give him more information? There's a lot of cool mechanics emerging, interaction mechanics emerging for this game. So we built some agents to play that using Ocean, also presented at CAG. I helped to organize the GTMC competition that I can design Minecraft. So there's a website if you want more details, but the basic idea is that you receive a map that you have never seen. It's an unpopulated map, and you have to build a set on frame. The thing that I'm currently working on is trying to capture a human intuition regarding building content. So you look at a new map, these are much of the new map, and people might say, oh, this map is bad for early versions because the bases are too well attended. They might say it's good for macro games, though, instead. They're good for flying units, or fighting happening on this choke point, or Zerg is OP in this map, is nerf. So we want to build an AI system that can emulate this kind of gameplay knowledge from a map. And we're going to go with a data-driven approach. So basically, we have map features on one side that we extract from the river maps, and our prediction targets on the other side that are things like average game length, the places where that's happening in the map, the usage of each unit or the mean rate of each race, and we're trying to build a machine learning model that predicts the second from the first. So looking at the map drawing, how can we predict this feature? And as this is just the start, it's quite interesting for game designers because as you generate content, you want to have a notion, an intuition of how the game will play out in that content. So this first aspect of reviewing is going in that direction of how designers evaluate the content before actually releasing them. And that's future steps, there's a lot. There's I'll actually do the method to put these variable maps. That's right now we're just doing analysis on existing maps. The user interface itself, integrating the prediction of these methods that I just talked about, and building a model of user preferences and using user studies to validate the system. So, thank you.
Questions?
Is there a danger if you're using a supervised learning approach to estimate some of these things that they're not right, but the designer takes it as being correct, and then they sort of release a broken level or easily breakable level?
So since we still haven't done the experiment, we don't know which of these metrics we actually can predict. Maybe some of them these are too hard. So we would use some sort of cross-validation. So we have some methods that are used for training, some methods that are used for validation, and see how well we can predict these metrics from the game map, and then hope that if you can predict these unseen maps that already exist in future maps that have never seen, the methods will work well. But so yeah, this is a broad danger, and we don't yet know if this will work necessarily. So we're going to keep doing.
Any other questions? Right. So I do have a question. So towards the end, you mentioned that you're going to focus on all of these metrics, like this map is not good for micro or whatever. So are those metrics that you're considering you are going to define those metrics, or are you expecting your system to come up with those metrics by analyzing them?
I think, oh, sorry. So the question was where I'm going to define these metrics, such as the get map is good for macro or for rushes, or I'm going to let the system come up with the metrics itself. So I think that since we don't even know if it will work, because maybe it's too complex to predict, we'll start by trying to predict metrics that we have previously defined. So for example, I'm using game length here as a proxy for whether the map is good for aggressive or controlling strategies. It's not like 100% correct, but it's a proxy. If it works very well, we can look at other things, such as unit composition also might help in that regard, because if you have more units, then you can infer that the map was good for economic play. And maybe even do unsupervised approach to that the system come up with its prediction target by itself. So it's possible.
Alright, so if it's very quick.
Have you considered using AIs to simulate the gameplay?
So we have, so here I have kind of a little bit. So two possible approaches would be simulation driven, which would be that. So instead of like relying on the data, I put a bot to play the map and extract those metrics from me. But current StarCraft bots don't play that well compared to humans, which might be a problem. So the bot plays in a way, maybe the bot is playing early commercials because that's all that it can do reasonably well. So we could do that and try to see whether the metrics like expected from replays and from bot matches work around the same level, but there's a big there, so that's why we're first starting with replays. Yeah.
Alright, so nice, thanks everyone again.
So moving into labs right now for medical consortium students, also for mentors. I believe Jonathan McCoy, one of the co-chairs, is going to be out right back there. He's going to show you where your lunch is. Everyone else is on their own lunch. And also, if anyone has a HDMI to VGA adapter, I think Josh would be a friend. So please see him if you have one of those, and we'll see you back here after lunch for the 6:30.